Hello, YouTube learners and students. This is Dr. Satish Singhal, PhD, Professor of Computer Science, El Camino College, Torrance, California. Today I'm going to talk about searching and sorting, video 1. In this one, we'll confine ourselves to just one searching technology called linear search, and there'll be other technology like binary search. There will still be linear search of array of structs and all that. So I don't know how many video I'll make in this series, could be 4 or 5, but we'll go. Let's look at the background first. Today all business decisions are data driven. Businesses make decisions after querying large amount of data to discern pattern in the data, and typical data queries may be searching for a key in vast amount of data. Larger the amount of data, slower will be the process of searching a single key in it. For example, let's say you place an order on an online store and you'll get an order number in the email. Let's say your stuff didn't come, you will call the online store and say, hey, my stuff didn't come, and they'll say, okay, can you please tell me your order number? And once you tell order number, they will search your order number in their computer. More than likely, order number is stored in some sort of list, could be an array, could be linked list, could be some other list, and once they find the match, they will locate your order number and talk to you about that. Okay, that's one example. If number of orders are huge, obviously it's going to take them a little bit longer. Okay, so that's one example of searching for a key. The other type of search that is done, or query more importantly, on the data is finding common themes in data. Example would be, for a business, what percentage of customers live in a particular state, zip code, or what percentage of customers use Visa card for purchase, how many use MasterCard, and how many just pay directly from their bank account number. Another could be finding exceptions in the data, like how many of our customers who get our catalog have never ordered anything. This is a very small list. Okay, this list could contain 100,000 different type of searches, but I just wanted to give you an example. Okay, so what is the conclusion of all this? Conclusion: searching data for a key or themes is a very common software practice, and one such technology is linear search. We're going to describe linear search in a lot of detail in this video, so let's start building towards that. In this technology, software starts searching for the data, for example, stored in the array, from the first array cell with index 0, and keeps searching sequentially until key is found, and after that search is terminated. If search continues until the last filled array element and key is not found, then key is not in the array. So you can say, okay, how did data get in the array? Well, this is typically how it's done. Your data will be in a text file or in a database, some storage facility on the hard drive. It's read into an array. In our case, could be read into other data structure like linked list and all that. And then software iterates through this structure, this list, to search for the data. We'll demo that very soon in a minute. The linear search technology has this speed that is dependent on the size of the array. Since key we are looking for can be at worst may not even be in the array, this search technology gets slower and slower on an average as we search larger and larger array. Okay, so that's the foundation of our discussion today. Now I'm going to show you a pictorial representation, which we later on will show in the code as well, of the linear search technology. Imagine that we have names of friends in a file and we read them into array. The array with names of 10 friends may look like this. So focus on this green band, that's our array. So names are like Richa, Natasha, Sasha, Donna, Tim, John, Masha, Adam, Zach, and Anil. And I on purpose did them in lowercase because when I run my program, I don't want to get into the problem of case sensitivity. Uh, in C++, equal operator for string is not case insensitive. So that's why for now I'm just going to do the case insensitive, actually lowercase. And notice this will be, if I call this array as friends, Richa will be friends 0, Natasha will be friends 1, Shasha will be friends 2, and so on. And there are 10 of them, so Anil will be friends 9. So suppose we need to search for the name John, that's my key, then that's how it will work. I'll iterate the array through a loop and I'll look for match between John and any element in the array. So I look at the friends 0, well Richa and John are not matching. So I go to the next one, Natasha and John are not matching. Then I go to the next one, Shasha and John are not matching. Same way Donna, Tim are not matching either. But when I go to friends 5, John and John, they're matching. Well, I found it. And I can terminate my search right here. Okay. But let's say I look for the name Alan. Well, there's no match with Richa, friend 0, no match with Natasha, no match with Shasha, and we can just keep going, no match, no match, no match. And then I didn't find it. So there's no match with any of the names in the list array. So in that case, I'll say, okay, I didn't find Alan in the array. And that would be obviously the worst case. Richa will be the best case. So if you take last element, which is n minus 1, and first element, which is 0, so n minus 1 divided by 2 will be approximately n by 2. That's the average search time. And if array is very, very large, if n is in like millions, well then n divided by 2 will not be that different. So we can say in this case, search speed is proportional to the size of the array, approximately. Okay, so that's the pictorial representation. So let's say, can we build an algorithm which is data independent for the linear search, data type independent, and that algorithm is right here. So since I need to terminate searching when I found the key, I set a boolean variable found to false, n is the length of the array, and I'll have this kind of for loop, index 0 to index less than 1, and not found. So found was false, not found will be true, and index was 0, 0 less than n will be true also. So I'll enter the loop, and then I do a match using if statement. If key that I'm looking for equals ARR index, value in the array. So example would be, if I'm looking for the John, and first time I look at Richa, and there's no match. So in that case, this if statement will be false, and I will not set found to true. Well, then I'll move to number 1. Number 1, if n is 10, true, and I still have not found it. But let's say I'm looking for iterating to, and I'm looking for John, I'm iterating to index 5. Well, then I found it, and then key and the friends 0, friends 5. Was it friends 5? Yeah. Well, then there is a match, and then I'll send the found to true, and then not found will become false, and then I'll exit the loop. Okay, so this is very, very simple algorithm using the for loop. There are many variations in this one. And there will be source code here. I can show it here, or I can show it in my compiler Xcode. So that algorithm converts into source code like this one. Here we are passing array to a function and passing key also to a function and logical length of the array. We don't have to look for the physical length of the array if all array elements are sequentially occupied. We just need to look at for logical length. So the reason I put const, because I don't want linear search function to alter the array, and also I don't want it to alter my key. So that's why I have the const passed by reference to save on the memory, and const array so that array is not altered. And I do exactly the same thing that I showed in the algorithm. I set the boolean found to false, and I do exactly the same thing, bool found to false. And then I do the same loop as I showed earlier for int index equal to 0, index less than length, and not found. Notice found was set to false, not found will be true. Index is set to 0, length is at least 10, can be 0. We don't have 0 length arrays. So first time this is true, this boolean composite boolean condition is true. Then I start to check the names in index 0 with the key. If there's no match, this will not be executed, and then I'll reach to index 1 and so on. So this will not execute until as long as this is false. Well, when would this be true? When I found it. Okay, when name stored in the array is same as key, then this will be true. Then I set the found to true, and not true will be false. That's when I exit the loop. Okay, and then I return the found, which was set to false but modifies to true, and in that case true will be returned. But if I iterate through the entire array, when this condition becomes false and this condition always remains false all through, then this remains false, then I'm going to return the false. Okay, so this is pretty simple. I'm going to show you this code in Xcode, and we'll discuss it there as well. So let's go to Xcode. Okay, so here first I create size max 10. That's exactly the prototype of the function I showed you in the Word document. And I set the array friends. I hard coded. You can read it from a file. It's the same thing, but didn't want to show you that much code. So I have the same array that I showed you here, exactly the same one. This one. So, and then I do the same, do a loop to do the search. But let me show you this function one more time. The same thing. I said found to false, index 0, index less than length, this length, and not found. Found will be, not found will be true. So this part will be true. If, as long as length is more than 0, this will be true. And I'll do exactly the loop I discussed earlier. I match the array element with the key. If there's no match, I'll go to the next index, next, until I find the match. If match is found, then I'll set the found to true. Not found, not true will be false. I'll exit the loop, and then I return the updated value of the found, which will be otherwise false if this condition was never true. Okay, so let's run this. Here I've done more code. I ask person to enter the name of a friend. I store that. Then I call the linear search function that I just showed you a few times. And if it's found, then I tell them, hey, it's in the list. Otherwise, say it's not in the list. And if they want to do the more search, then I can enter 0 to continue or 1 to exit. Notice that done 0 will be false and not false will be true. So I'll continue this loop. So pay some attention to this loop also. You'll get the code, this code as well, uploaded to your class website. But if they enter 1, done gets a value of 1, that is true, not true will be false, and I'll exit the loop. Okay, let's run this program. Okay, so we're seeing all the names here, but imagine we are not looking at them and we are just typing a name. So I type name Natasha, and Natasha is actually in the array, and it says name Natasha in the list. And I want to continue search, so I'll print 0 for that. And this time I say I want to see Anil, but Anil is in the list too, and we can see right here. Well, let's say I want to look at name Alan. And Alan is not in the list, you can see that, and that time found will be false, and then else block will execute, because if this is false, else will execute, and else block executes, and it says name Alan is not in the list. So that's the principle of linear search. The most important thing about linear search is that its speed is almost on an average is proportional to length of the array divided by 2. But sometimes we want to see what is the worst performance of an algorithm. Well, in that case, it may not be there, or it may be in the last element. Then it's proportional to size of the array, which is n. This worst case performance is called big O, performance of an algorithm. You'll learn about that a lot in data structure class, CS2. But until then, you just remember the worst performance is, we analyze for the worst performance, we analyze for the average performance. Worst performance in linear search is proportional to the size of the array. Time taken, average is size of the array divided by 2. Okay, that's one example of the linear search function. I'll take another example in the next video. Hopefully you understood this quite well. And that's the end of video number 1. Okay, so I'll meet you in the next video. Thank you.